This video covers Lesson 5-4 for Secondary 1 Math, Scatter Plots.
Okay. Warm-up 5-4. The following table lists the approximate price of crude oil. The X value represents the number of days since October 1st, 2014. In number 1, we're going to use these tables. This is one table. It's just been broken up into two pieces. Okay? And we're going to decide, is the data linear or exponential? So a quick way that we can check to decide if this is linear or exponential is look at the change in X and the change in Y. Here our change in X is from 5 to 36, which is about 30. If we look from 89 to 78, we find that we have a change of about 20. Now, looking at our second part of this same table, we go from 40 to 62. Again, that's a change of about 20. And then 77 to 67 is about a change of 10. So if we write these as a slope, and look at the change, that would be 10 over 20, which is 1/2. And 20 over 30, which is 2/3. And since those are pretty close to the same, right, 0.6 versus 0.5, very close, we could probably say that this is a linear relationship. And so we're going to say linear. Now we're going to use our graphing calculators, if you have one, or the Desmos.com calculator, and we're going to write the equation for the line of best fit or curve of best fit. We're going to find our correlation coefficient, okay, describe the correlation, and other things about that. So let's go ahead and flip over to our Desmos.com calculator. So remember, as we use this Desmos.com calculator, a few things. The first one is we've got to create a table to enter the information. So we're going to click on this plus sign and go down to table, and that's created this table. Now the next thing you're going to want to do is put in all the information from the table in the warm-up. That means both parts of the table. Don't only do one side or else it'll throw things off. So go ahead, you're going to pause the video, enter that information in the table, and then hit play. So pause the video. Now that you have all the information in the table, we're going to go ahead and at least look at it. But real quick, we're just going to set up our mins and maxes for the x-axis. So we're just going to go from 0 to 65 to capture all the x values in our table. And then on the y values, we'll go ahead and go from 50, well, maybe 60 to 90 here to capture all of those. And we can kind of see what's happening here as we see this square that Desmos is giving us. It's looking pretty linear here. We got kind of a curve, but then it changes the type of curve and curves back down. So probably not an exponential here. Definitely looking more of a linear pattern. Maybe not a super strong correlation. But we can go ahead and double check. We can say Y1, use our similarity sign in that top left corner of your keyboard, and then go MX and then the plus the B. And then you got x1, plus b. And then we get this correlation coefficient of negative 0.9463. Now, if I just quickly modify this and go AB to the x1 power and turn on my log mode, you'll notice I get a 0.938, which is less than the linear. So I'm definitely going to go with a linear equation for my line of best fit. So again, that was MX1 plus B. And here's the information that we're going to use as we flip back into our notes and write our equation. Up here at the top, you'll see the information that we gathered from the Desmos.com calculator. And we're going to write our equation for the line of best fit, and we're going to round to the nearest hundredth. Okay? And so looking at this, we're going to start out, we'll have y equals, and then our slope, nearest hundredth, is 2 decimal places. So it's going to be negative 0.32. And that's going to be multiplied to x. And then we're going to add our y-intercept of 88.73. Okay, so there's our equation for our line of best fit. Next, we're going to look at the correlation coefficient. That's the R value. And we're going to round this to the nearest hundredth. So we're going 2 decimal places, 9, 4, but the 6 tells us to round that up. So it's going to be negative 0.95. So what does that correlation mean? Well, the correlation then we would describe as strong and then negative because the value is negative. Strong because we're close to the 1, okay, at 0.95, or negative 1 at negative 0.95. And it's a negative number, so we have a strong negative correlation. Number 5, does this relationship have a positive, negative, or no correlation? And we already said that this is a negative correlation, okay? And how can we tell that this is going to be a negative correlation? The first way we can decide that these are going to have a negative correlation is by looking at our slope. And since that slope is negative, then our correlation is also going to be a negative. Now, the second way that we can identify this is by looking at our table. Because in the table, we'll notice that the y values are decreasing as the x values are increasing. So one is increasing while the other is decreasing. That's going to be a negative correlation. The last way is that we could look at our correlation coefficient. Right up here, you see our correlation coefficient. And since it's a negative number, that's another way that we can identify this as a negative correlation. Number 6, determine which table has a linear relationship and which table has an exponential relationship. So glancing at these, you might say, oh, they're both increasing quite a bit. What's going on here? So we take a little bit closer look at these and we say, all right, if I'm looking at the changes in y, it looks like all the changes in x's are 1 for both tables. So I look at the change in the y's. And so we say 4 to 9, that's 5.2. This next change is going to be 11.8, right? The next one would be 28, then 63. Then we have 145, and then it's 333. And you can see how that's changing and growing and growing and growing, bigger and bigger. Over here, again, our change in x, just like in the first one, is 1 every time, okay? And so then I look at the y's and I say, okay, this is 20. This is, 19? Right here we have 22. Then it's 21. Then we have 17, 21, 23. Okay, so this is pretty consistent. And so this one will be our exponential. The first one is the exponential. And the second one is going to be linear. And we have to decide, hey, how can I support this? How am I going to justify saying that this is the case? Well, we can say that this first one is exponential because we are about doubling the change each time. So the y value almost double every change of 1 in x. So again, it's exponential because the y values almost double every change of 1 in x. Now the second table is linear because the change in the y values is about 20 every single time. So we can say that it's linear, the change in the y values is about 20 every change of 1 in x. Okay, so lesson 5-4, scatter plots. So here we're going to be entering the data into our Desmos.com calculator for each situation, and we're going to decide if it's linear or exponential. We're going to write an equation for the line or curve of best fit, find the correlation coefficient, and describe what the slope or rate of growth and the Y-intercept or initial value represent. Remember that the first column is always going to be our x value, so that would be time in this case in minutes. And the second column is going to be our y value when we're dealing with a vertical table. So in this case, that would be the number of fish tacos sold during lunch. Now when we enter this information, we are going to try to decide if that's linear or exponential. But we could look at that right now and decide, or at least have an idea of what we think. So here we have a change of 5. Here's a change of 2. A change of 8, sorry. Here we have a change of 3. Here's a change of 20. And so looking at the other side of this, we have a change of 1, a change of 2, we have a change of 4, and then we have a change of 2, a change of 7. So you can kind of see as the larger numbers on the y side, we get larger numbers on the x side for the most part. and we're going to see that kind of pattern. So we might lean towards saying that this is linear, okay? And I can always just double check it with graphing it on the Desmos.com calculator. So go ahead and flip over to the Desmos.com calculator. Okay, so here we are on our Desmos.com calculator. Remember, we're just going to delete what's already here, clear it out, and start over. So we're going to create a table, clicking the plus button, putting it down. We're going to enter our information. Okay, so you're going to pause the video, enter all the information from the table, and set your window so you can kind of see what it looks like. So go ahead and pause the video. Okay, so here you go. You can see my window and my table that we put in, and you can kind of see this is following a straight line. So we're going to say that definitely this is linear, like we thought it was, okay, originally, based on seeing that our change was typically, not a lot different. We were looking at a change of 1 or 2, maybe up to 5 was the max, okay, but more around that 1 to 2 to 3 range. So we're going to go ahead and type in our linear equation. Remember to do this, we go y, then the 1, then you go shift and the button right below your escape or above your tab for the similarity sign. And then you're going to go mx1 and then the plus sign b. And it gives us our information to write our equation and talk more about this equation and the situation we're dealing with. So we decided that this was linear because we're changing about the same amount every time. And when we looked at it on the Desmos.com calculator, we could see that linear pattern. Noticing also here our correlation coefficient, the R, was really, really strong, which indicates that it's probably going to be linear as well. Now, this is the information from our Desmos.com calculator up here, and we're going to use this. Now we're going to be rounding to the nearest whole number for everything. So we're going to write our equation, y equals, and then our slope, m, is 2.2, so 2 times x, plus our b is 2.9, which rounds to 3. Now our correlation coefficient, we're going to round to the nearest thousandth, so that's 3 decimal places, so 1, 2, 3. And then that second 7 is the 10,000th place. So we're going to round up. So our correlation coefficient is 0.998. Okay, using this equation and looking at our equation, we're going to write a sentence explaining what the slope or rate of growth represents. Remember, your slope is what's next to the x, and that's 2. So it might be helpful to write this as a fraction and think of this as 2 over 1. And 1, our units is minutes. Our units are minutes. So 1 minute, and that's 2 fish tacos that are sold. Okay? So 2 fish tacos sold for every minute. So that's what we're going to write. So I wrote, about 2 fish tacos are sold every minute of lunch. Number 5, write a sentence explaining what the y-intercept or initial value represents. Well, our y-intercept is 3. Which means that at time 0, or at the beginning of lunch, they had already sold 3 fish tacos. Okay, so the next situation is again with fish, but here, again, we're going to have x as our time, but this time it's in years, and the y is going to be the number of fish in a no fishing pond. And we've got to decide if this is going to be linear or is this going to be exponential. So just glancing at it, all the x values are changing by 1. And then we can notice that from 6 to 12, that's like doubling. We're multiplying it by 2. But then this 11 and 12 are kind of the same. But if we go to the next 2, that's almost doubling again. It's like we're multiplying these by 2. Not adding 2 here, but multiplying them by 2. Then if I look at the next one, again, we're changing, right? From 18 to like this 30 and 28. It's almost adding a 10 again here, okay? And here, that doubling was about 10. Here was 6. And then down here, you even notice it some more as we look at like the 120 to 150 going to 240. That's, again, almost doubling. So just because we're seeing this kind of pattern of almost doubling a lot, we're going to go and say that this is exponential. And we can double check as we use the Desmos.com calculator, which we're going to do now to help us write the equation of the curve of best fit. Okay, so again, I'm just clearing out my information I already had. Going to set up my new table. And we're going to go ahead and enter this information from the table with the time in years and the number of fish in the no fishing pond. So pause the video, enter the information into the table, and create a window so you can kind of see what that looks like. So pause the video. Okay, so now that you have your table and you've changed your window, you'll see something like this, where you can tell, and I'll zoom out just a little bit so you can see it, it's curving up. It's growing more and more as we gain more fish. There's more that or there's more fish being added to the pond. Um, so here we can see that with this nice curve. Okay, so we definitely can say with confidence now, seeing the curve, that this is definitely going to be exponential. And remember, we could always double check by just typing it in, y equals, or not y equals, y1 similarity sign, mx plus b, mx1, always forget that one, okay? It's 0.8766, and that doesn't follow our trend very well. So 0.87, we'll just think about that. If we change this to the exponential, AB, right, then the caret symbol above the 6, so shift 6, x1, and log mode, you can see that this correlation is 9.8. So definitely stronger, definitely an exponential situation. So we're going to take this information right here and we're going to write our equation for the curve of best fit and write our correlation coefficient in our notes. Place the information from our Desmos.com calculator right down here. And we're going to write our equation. Now, we're going to round the slope or our rate, which we're going to refer to the rate, right, to the nearest hundredth. The Y-intercept, our initial value, is going to be to the nearest whole number. So we're going to write it in the same form as it says here, Y, but here we're going to have the equal sign. Our A, we're rounding to the nearest whole, so it's going to round up to 5. And then we're going to have in parentheses, rounding to the nearest hundredth, 2 decimal places, 0.37. The 4 tells us after that to stay the same. So it's just going to be 1.37. Sorry, 1.37. And then we're going to raise it to the xth power. Our correlation coefficient, or the R, is going to be 0.98. And that 3 after the 8 tells us to keep it the same when we're rounding to the nearest hundredth. Okay, so number 9 and 10. Number 9 says, write a sentence explaining what the slope or rate of growth represents. Now remember, if we're talking about rate of growth, that's not 1.37. That's going to be our growth factor. So our rate of growth is just the 0.37. So that's 37%. So what we're going to say about this growth factor and the situation is that the number of fish in the pond increases 37% each year. Okay, number 10, write a sentence explaining what the y-intercept or initial value represents. So our initial value was 5, which means that that's a point, and the x value of 0 would be a y value of 5. So at time 0 years, the number of fish in the pond would have been 5. So we're saying that at the beginning, there are 5 fish in the pond. Okay, our next situation, we're going to talk about the number of bears in the watering hole and the number of fish in the watering hole. And we have to decide if this data is linear or exponential. So let's just look at our changes here. This is a change of 3 and 1 and 4 and 2 and 5. So not super consistent here, 2 and 2. But our change here was 300. Then we went to a change of 400. Then a change of 50. Then we went from there to a change of 450. And then a change of 200. And a change of, what is that going to be, 450. And then we have a change of like 130. So looking at those changes and the changes above, I'm guessing this is probably going to be a linear situation because our changes aren't too crazy different. There are some changes for sure, and they're not quite the same. So 3 over 300, 1 over 400 seems a little weird. But we're going to have that discrepancy with scatter plots. And so I don't see a significant change in my y's versus the x's, where it's steadily growing to be a larger and larger change or smaller and smaller change. So I'm going to guess that this is going to be linear, and then we're going to use our Desmos.com calculator to double check. Okay, so I already deleted everything. I have a clean slate. We go plus to table. And remember here that our table was horizontal. And so when I change it to a vertical table, I have to remember which one's X and which is Y. And X is going to be the number of bears at the watering hole, or the top part of our table. So we're going to start out with 2. We're going to go to 5, 6, and so on. Now, the Y value is the bottom, or the number of fish in the watering hole, which started out with 2,000. So go ahead and pause the video, enter the information into the table, and set your settings so that you can see your graph. So go ahead and pause the video and hit play when you are done. So a quick reminder on how to set up that window. If you click over here on the wrench, it pops up. Then you have go a little smaller than your smallest X value in the table, a little larger than the largest one. So like 0 to 22. The Y values, you can do the same thing here. And so the smallest was 22, so like 20, going up to my largest Y value, just above that, so like 2020. Sure. And then I can see it better. Again, I can zoom out to kind of help me see this. But you can tell like they're shifting, but this is a pretty linear change here. It doesn't have a nice curve to it, which was what we would expect for an exponential. And so we're going to go ahead and type in for our linear equation in that second box, y, and then that y1, and then the similarity sign. Then you go mx1 plus b. And you see here, pretty strong correlation, negative 0.9815, okay? And so we're going to take that information over and write our equation for our line of best fit. Okay, so now that we've confirmed that this is a linear situation using our Desmos.com calculator, we can take this information that we gathered and write our equation for the line of best fit. And we're going to round everything to the nearest whole. So we're going to start out here as writing y equals, and then our slope is negative 99.5, so we're going to round that up to negative 100 times x. And our value of b is 2,122.4. So rounding to the nearest whole, we'll say 2,122. Our correlation coefficient right here is negative 0.9 and then 8. If we go to the next decimal, that's 1. Oh, good. So I didn't make a mistake. It is 0.98, negative 0.98. Okay, writing a sentence explaining what the slope or rate of decay represents. So our slope here is saying that for every one bear, think about the fraction here, negative 100 over 1. One bear, negative 100 fish. So we can say the number of fish decreases by 100 fish for every additional bear at the watering hole. Number 15, write a sentence explaining the initial value. That's the 2,122. So we can say, with no bears at the watering hole, there would be about 2,122 fish. Okay, our last situation. We got time in minutes and the number of fish left at the fish market. So first we have to decide if this data is linear or exponential. And so looking at this, we look at the change in x and the change in y. So our change in x, it looks like we got a change of 2, a change of 1, a change of 2, a change of 1, a change of 1, a change of 2, a change of 4, a change of 1, a change of 3, a change of 2. So pretty consistent here. So that's good. Now we're going to look and see if it stays consistent on the other side. So this first one is 28. Then we're going down by 15. And then we're going down by 15. And then we're going down here by 3. And then about, well, that's at 9. And then 8. And then we're going 9. And then 2. And then 4. And then 1. And you can see this steadily changing and going down. I mean, there's this outlier here, but other than that, it's looking pretty consistent as it decreases. And so I'm going to think that instead of changing 28, it's changing by 1s and 2s and 4s. This is probably going to lean more towards an exponential situation. Now we can double check it, but I'm pretty sure that's going to be the case when we see that change in X not really changing much, but the Y is changing significantly, or in a greater amount, indicating exponential. So let's flip over to our Desmos.com calculator. So right here in our Desmos.com calculator, we're going to hit the plus sign, go to table, and start filling out this table. Remembering that the top row of our table in our notes is going to be the X, which is time in minutes, and the bottom one will be the Y, which is going to be number of fish. So we're going to go 1 here for our X value. The Y value is 98. So make sure you keep that straight as you're entering it. But go ahead, enter the information in the table, make sure you can see your graph, and then hit play to resume the video. So pause it now and do those two things. Okay, so here we are. I got the table in. You got your graph, and you can kind of see here, this is not going to be linear. It's got a nice curve to it as it's decreasing. So we can already decide that this is definitely going to have a negative correlation coefficient or negative correlation. To write our equation, since this is an exponential, which we assumed or we thought it was, we're going to go y1, then that similarity sign. Then we're going to go a, b, the caret, which is shift 6. And then we're going to go x1. And then we're going to click on this log mode so we get all the information. And you can see that it's following that trend really, really well, which is why it's such a strong correlation coefficient here of r. So there's our information. We're going to take that information and finish our notes here dealing with this situation. Okay, so now that we have this information here that has been given to us through the Desmos.com calculator, we're going to write our equation for the curve of best fit. And we're going to round our rate to the nearest hundredth, and we're going to round the initial value to the nearest whole. And so our initial value is right here, 113.3. So we're going to start out by saying this is y equals 113. And then our rate is going to be the 0.843. So hundredths is going to be where the 4 is, but the 3 tells us to stay where we have it. So it's going to be 0.84 raised to the xth power. Okay, so now we have our equation. Our correlation coefficient is right here. That's the negative 0.99. Now, thousandths place is going to be 3, so that third 9, the 1 tells us to stay the same, so it's just going to be negative 0.999, which is a really strong negative correlation. Okay, so now we're going to write a sentence explaining what the slope, in this case, the rate of decay, represents. So remembering, we got to go back to this idea. Remember, this is not our rate, actually. This is actually our decay factor. And if we want to find the decay rate, we got to take 1 minus that 0.84, which is going to give us 0.16. Now, if that's going to be our rate of decay, we're going to say that the number of fish at the market decreases 16% every minute. So again, we're going to say the number of fish at the market decreases 16% every minute. Okay, now we need to write a sentence explaining what the y-intercept or the initial value represents. And we found our initial value to be the 113. And so we're saying at 0 minutes, because that's our x value, remember this is a point, so 0, 113. So at 0 minutes, there were 113 fish at the marketplace. Or we could say, at the beginning, or when the market opened, there were 113 fish.
This concludes the video of Lesson 5-4 for Secondary 1 Math, Scatter Plots.